During inflation, the matter field phi will slowly change to reduce the potential V of the field. One can think of the field as slowly rolling down the hill, and this is called slow roll inflation. The rate, h, of expansion of the universe will be almost constant, but will slowly decrease. Inflation will end when the field, phi, is near the minimum of the potential and starts to oscillate about the minimum. The energy in the field, phi, has been converted into a hot plasma of other particles, and the universe is set to reheat. On the other hand, if the value of phi0 is small, the universe will not inflate, but will collapse to a singularity in a tiny fraction of a second. Quantum gravity predicts many possible mysteries in many possible states at later times, that is, at times like the present, long after their creation. Most of these states will be quite unlike the universe we observe, and quite unsuitable for the existence of any form of life. Only a very few would allow creatures, like us, to exist. Thus our presence selects out from this vast array only those universes that are compatible with our existence. Although we are puny and insignificant on the scale of the cosmos, this makes us, in a sense, lords of creation. Recent measurements of Higgs field have raised the possibility that the field may not be in the lowest energy state. If this is the case, the field is in a false vacuum state. It can decay to the true vacuum by quantum fluctuations forming a bubble of the true vacuum, which would expand at the speed of light. We would not see it coming. But if it hit us, it would wipe us out. Fortunately, the probable lifetime for false vacuum decay is longer than the age of the universe. Although inflation produces a universe that is nearly the same everywhere and in every direction, there will be local irregularities produced by quantum fluctuations. Perturbations of the homogeneous and isotropic universe come in two kinds. Scalar perturbations, which correspond to variations in the density and rate of expansion, and tensor perturbations, which correspond to gravitational waves. Both kinds of perturbations have a common cause. This is basically the same mechanism as so-called Hawking radiation from a black hole horizon, which I predicted some time ago. Except that this time it comes from the cosmological horizon, beyond which one can see events no matter how long one waits. radiation from the cosmological horizon has a temperature h over 2 pi, where h is the rate of expansion of the universe. Although the density fluctuations and gravitational waves have a common origin as effective thermal fluctuations in the very early universe, there is an important difference. The scalar density perturbations are caused by quantum fluctuations in the matter field, phi, which will displace the surfaces of constant phi from where they would have been. On the other hand, the gravitational waves don't depend on phi, but arise directly as fluctuations in the inflating universe, with temperature h over 2 pi. The tensor perturbations will therefore be weaker than the scalar perturbations by a factor, r equals 1 over partial d over partial phi. The scalar perturbations were first calculated at a workshop by Bell in Cambridge in 1982. This was 10 years before fluctuations in the microwave diet were discovered by the Capri satellite in 1993, so theory was way ahead of experiment. Cosmology became a precision science another 10 years later, in 2003, with the first results from the WMAP satellite, which confirmed the predicted, almost scale-invariant wavelength dependence of the scalar perturbations. WMAP produced a wonderful map of the temperature of the cosmic microwave diet, a snapshot of the universe at about 300,000ths of its present age. The irregularities you see are predicted by inflation, and they mean that some regions of the universe had a slightly higher density than others. The gravitational attraction of the extra density slows the expansion of that region, and can eventually cause it to collapse to form galaxies and stars. So look carefully at the map of the microwave diet. It is the blueprint for all the structure in the universe. We are the product of quantum fluctuations in the very early universe. God really does play dice. Superseding WMAP, today there is a planned satellite with a much higher resolution map of the universe you see here on the screen. The analysis of the planned data has shown remarkable agreement with the predictions of the simplest models of inflation. The green line here